Welcome back, everyone. This is probably the last video on the Holder inequalities proof, and so as I promised you guys, I'm gonna show you guys two variations of these inequalities, and you guys can use both variation. Which one works best for you? Okay. So the first variation is you doing accordingly to the question. So let me write down. First variation. Doing accord similar to what you've been asked. Yeah, let's put that away. To what you have been asked for. Okay, so what you've been asked for, you asked to prove this form, right? You see this form right here. Okay, so you have, so what I'm gonna do is I'm gonna set the constraint right there. So you have to make it similar to what the problem asks you. That's how you get an A. You have to arrive at the exactly the result that the problem give you. Okay, so what you're gonna do is this. You set the constraint, so you'd be like, let 1 over P plus 1 over Q equal to 1. Okay, so what will we have? We will have P plus Q over PQ equal to 1, right? So what we have, if you flip them, PQ over P plus Q will equal to 1. Okay, so this being said, you also have what? If you divide both sides by P, you have Q over P plus Q equal 1 over P. This expression right here, if you divide both sides by Q, you have P over P plus Q equal to 1 over Q. Okay, and then you be like, this is A, this is B, this is C, and this is 2. I'll call this 2. Okay, you be like, substitute A, B, and C into 2. We have. Okay, so this guy right here, this term right here become this term. Okay, this term right here become that term. And oh, I have blue. Beautiful. Have to be different colors, right? This term right there become 1. Okay, so you just need to rewrite them. So if you rewrite them, you have, it's very similar. It's you see, it simplifies a lot. So you rewrite them, you have this summation of I equal 1 and xi to power p, and then that become 1 over p times summation of I equal 1 to the n of yi to the power of q times 1 over q greater than or equal to summation of xi yi I to the power of 1 n. Okay, so that is our first variation. So that's the first variation we have for Holder inequalities based on 2. Sorry guys, based on 2. Okay, but I'm gonna show you the second one, which is more intuitive. Okay, let me write down second variation. From 2, u power p plus q to both sides. I think this one is more intuitive. I mean, the problem is good, but I think this one is more intuitive when you actually do inequalities. This is just what the problem asks you to, but that's just my personal opinion. Okay, so if you power p plus q, both sides of part 2, you basically you can time the power to p plus q. So q over p plus q times p plus q will become what? It will become q, and similarly this one become p, and this one become pq. Okay, so this become p and this become pq. Okay, so you just rewrite them. You arrive at this. So you have summation of I equal 1 to n xi to the power p all the power q times summation of I equal 1 and yi to the power q 1 to the power p greater or equal to summation of I equal 1 and xi yi to the power of p q. Okay, I think this one makes more sense. So yeah, let me plug in, and this is no constraint. You see the difference is the difference between the this is pink. Let me. The difference between pink and red is that the pink one don't have any restraint. You see, there's no restraint. P and Q can be anything. But in order to use the red, 1 over your Q and your P have to satisfy this condition right here. You have to your P and your Q have to be a number such that 1 over P plus 1 over Q equal to 1, which is a constraint, right? Not freedom at all. But that's what the problem asks, so that's why we have to do it. But actually, in real life, I encourage you to do the pink, because P and Q can be any positive real number. I mean, it could be negative complex number too, but for the sake of this video, I would say it's not valid, and I'll encourage you to verify it for yourself, like to figure out how to do it with complex number and non-positive number, stuff like that. Okay, yeah. So just to make it apparent, I'm gonna give you example. Let's say that let me give you one example. Oh, wait, hang on. This is very important. Oh my god, I almost forgot. P and Q, actually there's a restraint. That restraint is P and Q had to be greater than 1. Okay? And positive. Yeah, but that's pretty much it. Yeah, P and Q have to be greater than 1. Oh my god. Forgot. Yeah, so it will work if that's the case. So let me give you an example. Like if P equal Q equal 2, you have what? You have summation of I equal 1 and xi square times summation of I equal 1 and yi square greater than or equal to summation of I equal 1 and xi yi square. Okay, and you can totally prove this for yourself. Like this is the if you take the root of both sides, you arrive at this. Oh, actually no, this is 2 times 2. Sorry, PQ is 2 times 2. This is 4. If you take the root, you take the square root of both sides, you arrive at this. xy square times summation I equal 1 to n yi square greater than or equal to summation of I equal 1 and I yi on this square. And this, my friend, is the famous Cauchy, hopefully Schwarz theorem, inequality. Yeah, this is the famous Cauchy-Schwarz inequality. It derived from Honder. You can prove it yourself too, but basically it's the special case of Honder. Okay, yeah, that's very much it. I would like to conclude our discussion on Honder inequalities, and I hope you guys found helpful, and I wish you have an amazing day. Thank you for your attention, and take care.